Draw the Lewis structure for this given formula. First, draw the Lewis structure and then find the electron pair geometry around the central atom, electron pair geometry and shape. Pause this video and first try it yourself. To draw the Lewis structure, first figure out the total number of valence electrons. Xenon is a noble gas. It's in group 18, so it has 8 valence electrons. Oxygen is in group 16. It has 6 valence electrons. And fluorine is in group 17. It has 7 valence electrons, but you have 4 fluorine atoms. Now take the total number of valence electrons. That's 42 valence electrons in total. Next, we are going to place the element, the atom with the lowest electronegativity in the center. And you know from periodic trends, oxygen and fluorine has higher electronegativities, so our central atom is going to be xenon. Now we can place the other atoms around xenon. 1 oxygen and 4 fluorine atoms. Then we can connect each atom with the central atom with a pair of electrons. So I'm going to use 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 valence electrons from these 42 valence electrons. Rest of the electrons I'm going to place around other atoms, all the atoms following the possible rules, following the octet rule and if possible expanded octet. Now I use 10 electrons, so 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32, 33, 34, 35, 36, 37, 38, 39, 40. Now I have used 40 out from this 42 total electrons. So that means I have 2 more electrons to place, and I know I cannot place any more electrons on oxygen or fluorine because they cannot have more than 8 electrons overall. Why is that? Oxygen and fluorine, they are in the second period. In the second period, they can have only a maximum of 8 electrons. Why is that? Going into more details, you have to know that in level 2 or the period 2, the orbitals you have is s and p orbitals. In s orbitals, you have 2 maximum electrons, and in p orbital, you have 3 p orbitals. So in each orbital you can have 2 electrons, so that is 6 total electrons in p. So collectively s and p you can have maximum of 8. The elements in period 2 do not have any d orbitals, any empty d orbitals, so they cannot have any more electrons than 8. So whatever the 2 remaining electrons, I've used 40 out from 42. The remaining 2 electrons I'm going to put it on xenon. I'm just going to put it in a different color so that you will see it clearly. Now my 42 valence electrons is complete. Now I have to think if this is the best Lewis structure I can come up with. In order to figure out if I have the best Lewis structure, I can calculate the formal charges. First, I will do the formal charge for fluorine. Considering fluorine atom, all these lone pairs on fluorine belong to fluorine, fully owned by fluorine. But in the case of these bonded electrons over here, only one can be assigned to fluorine atom. So fluorine, it should have 7 valence electrons, but in the Lewis structure that we have drawn, it is holding 7 valence electrons. So the formal charge of fluorine in this structure is going to be 0. And all the other fluorine atoms have the same environment. So all the other fluorine atoms also going to have a formal charge of 0. Now let's check xenon. Xenon has this lone pair marked in yellow color. So those 2 electrons are fully owned by xenon, and what else can be assigned is 1 electron per each single bond. Now let's calculate the formal charge for xenon. Xenon has 8 valence electrons around it, but in the structure we have drawn how many electrons is it holding. It is 1, 2, 1, 2, 3, 4, 5, 6, 7. So it is holding only 7 electrons. So in that case, xenon is going to have a +1 formal charge. Let's do the formal charge for oxygen. Consider the electrons around oxygen atom. Oxygen should have 6 valence electrons according to the periodic table, but in the structure we have drawn, it is containing 7 electrons around it. So oxygen is carrying a -1 formal charge. So overall, in the structure we have drawn here, we have this set of formal charges. Now let's do a small rearrangement in electrons and see if we can get a better set of formal charges while still following the octet rule. Now what I'm going to do here is I'm going to move a pair of electrons from oxygen. I'm going to move this pair of electrons between oxygen and xenon. Now my new setup is going to look like this. Now I can calculate the formal charge again. Now if I calculate the formal charge around oxygen, remember from each bond the atom owns only 1 electron. So I'm going to draw my line like this. So in the bond between oxygen and xenon, there are overall 4 electrons, but I'm going to assign only half of that for oxygen. Now let's calculate the formal charge. Oxygen has 6 valence electrons. In the Lewis structure that we have drawn, also there's 6 valence electrons. So now oxygen has the formal charge of 0. And what happened to xenon? Let's check the total number of electrons around xenon. Xenon has the valence number 8. And in the structure that we have drawn, now xenon has 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons in the structure we have drawn. So now xenon is also 0, and you can see we didn't do anything to fluorine atom. Fluorine is still 0. So the new structure we have drawn is the best Lewis structure for this given formula. Now I'm going to redraw this structure as a proper Lewis dot dash structure. I have a double bond between oxygen and xenon, and these are my remaining electrons. Now let's find out how many repulsive units we have around the central atom. How many VSEPR units we have around the central atom. This is 1, 2, 3, 4, 5. So we have 5 repulsive units. Oops, I made a mistake. I forgot to include the lone pair in here. So now we have actually 6 repulsive units. Now that's a good example of keeping tabs on what you're doing. When you're moving from one structure to the other one, you might end up losing electrons because you're making errors like I did. When you have 6 repulsive units, your electron pair geometry is octahedral. When you consider the shape, you actually remove the lone pair from your view. So let's say if we have octahedral shape like this, you have the central atom and the surrounding bonds, and then we are going to remove, let's say this is your lone pair, and I'm going to remove this from our picture. Now it kind of look like a square pyramid. It's a pyramid with a base in the square, base as a square, so your shape is a square pyramid. For the next question, we are going to draw the Lewis structure for this formula, N2O3. But in this case, I'm going to give you the rough skeleton. This is not the complete Lewis structure. It is just showing you how atoms are connected roughly. So you're supposed to come up with the correct Lewis structure. Again, pause the video and first try it yourself. First, let's find the total number of valence electrons. Nitrogen is in group 15. It has 5 valence electrons, but in the given formula we have 2 nitrogen atoms, and then oxygen in 16 group, it has 6 valence electrons, and here we have 3 oxygen atoms. So the total number of valence electrons is 28. Now I'm going to redraw the same connectivity. Now I'm going to connect each atom with a pair of electrons. 1, 2, 3, 4, 5, 6, 7, 8. That is pretty much the same connectivity shown here. Now I've used 8 out of 28. I'm going to fill in the rest. 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. Now when I look at the structure I came up with, things seems to be okay with oxygen because it has completed its octet, and it is true with the other oxygens. They all have completed the octet, and also this particular nitrogen. So they all seem to have completed their octet, but we have a huge problem with this nitrogen. It has not completed octet. It is holding only 4 electron. It is 4 electron deficient. And what we have to know is that elements in the second period, the elements carbon, nitrogen, oxygen, fluorine, those 4 elements will always go for an octet. So we need to fix this problem here in this nitrogen atom. Also, another way you can find out this is not the best Lewis structure you can come up with is the formal charges. If you do it, you will find oxygens are going to have a -1 charge, while this nitrogen is 0, but the electron deficient nitrogen is a +3 charge. Now nitrogen is an electronegative, very electronegative atom, and it doesn't like to hold this big positive charge. So we are going to go for another structure, and let's see how things are going to turn around. Instead of having these 2 electrons in this nitrogen, I'm going to put that pair of electron over here. So now what I'm going to put is those 2 electrons on this nitrogen, and let's do a formal charge calculation. The first oxygen atom, valence oxygen has 6 valence electrons, but this one is holding 7 electrons around it, so this oxygen carries the formal charge of -1. And the other oxygens are pretty similar, so other oxygens also carry the -1 charge. The nitrogen atom here, you can find 5 valence electrons around nitrogen, but in this structure you have only 3 electrons, so 5 minus 3, that is a +2 formal charge for that nitrogen atom. And next we can find the formal charge for this nitrogen atom. Nitrogen has 5 valence electrons. This nitrogen atom holds 1, 2, 3, 4 electrons, making the formal charge +1 for that nitrogen atom. Additionally, you can see now the 2 nitrogen atoms, they are holding only 6 electrons in the bonded state, like overall 6 electrons. Still it needs 2 more electrons to complete the octet. Now let's try to complete the octet for nitrogen. Let's move 2 electrons from this oxygen into here. So we can move this pair of electron there. So that will complete the octet of the first nitrogen atom. And to solve the problem on the other end, we can move this pair of electrons over there. You can either do this oxygen atom or the other one. It really doesn't matter which one you're doing, either this one or that one. You can move that, make that move. So once we move those electrons, we are going to get this kind of a structure. Now let's do another formal charge calculation. First, we'll try this oxygen atom. Oxygen has 6 valence electrons. In this structure, it is we can assign 1, 2, 3, 4, 5, 6 electrons. So the formal charge of this oxygen atom is 0. And this oxygen atom is very similar to this one. So we can assign the other double bonded oxygen also a 0 formal charge. What about the other oxygen atom? You can see it has the same electronic environment. Its formal charge is -1 again. Let's check the formal charges of nitrogen atoms. Consider this nitrogen atom 5. It's in this Lewis structure, it's holding 5 electrons. So the valence, the formal charge is going to be 0. What about the other nitrogen atom? In this structure, this nitrogen atom is holding 1, 2, 3, 4 electrons. So its formal charge is +1. You can see that in the first structure, the set of formal charges were -1, -1, -1, nitrogen +1, and +2. But in the second occasion, you have 0, 0, -1, 0, and a +1. And you can see in the second Lewis structure we came up with, we were able to have minimum with the smallest values for the formal charges. So we were able to get the minimum formal charge for atoms while following the octet rule. So we can say the second structure we came up with is the best Lewis structure for N2O3. But I'm going to make a small change. I'm going to put the bonds as the dashes. This is our correct Lewis dash dot structure. Let's find the proper Lewis structure for this formula. First, we'll find the Lewis structure, and then we'll find the electron pair geometry and shape. Chlorine is in group 17, so it has 7 valence electrons. Fluorine in the same group. Now we have 4 fluorine atoms, and also don't forget the +1 charge the overall molecule hold. So if it is a +1, you take off 1 electron. So the total number of valence electrons is 34. Chlorine will be our central atom. Fluorine is the most electronegative atom, and we know that fluorine can never be in a center. So I'm going to put chlorine in the center, place the other 4 atoms around it like this, and then connect them with a pair of electrons. 1 2 3 4 5 6 7 8 9 10 11 12 13 14 15 16 17 18 19 20 21 22 23 24 25 26 27 28 29 30 31 32. I have used 32 electrons from this 34. So where can I put the remaining 2 electrons? I cannot put it on fluorine because fluorine cannot hold more than 8. It's a period 2 element. It cannot hold more than 8 electrons. So the remaining 2 electrons I'm going to put on chlorine. Chlorine can have an expanded octet. It has empty d orbitals, so it can hold more than 8 electrons. If you do the formal charges, you will find that all the fluorine atoms have a formal charge of 0, while chlorine will hold the +1 formal charge. We can redraw the Lewis dot dash structure of chlorine like this. Now remember, I have placed my lone pair in the trigonal plane. Actually, I should have mentioned the electron pair geometry before mentioning the trigonal plane, counting the number of repulsive units. That's 1 2 3 4 5. You have 5 repulsive units. Five repulsive units, meaning your electron pair geometry is going to be trigonal bipyramidal. That's your electron pair geometry. In the trigonal bipyramidal geometry, you know you have a trigonal plane, which is this, and you have to know when we have only one lone pair in this geometry, we put the lone pair in the trigonal plane because that is how the lone pair can have maximum space for itself. Now that is the geometry. Geometry is taken considering all the bonds and the lone pairs, but shape is little bit different. When you take the shape, you can remove the lone pair from your mental picture. Don't remove it from the actual picture, otherwise it would be marked wrong, but just to visualize it, you can remove the lone pair from your picture and turn this molecule. It will look like a seesaw. So your shape will look like a seesaw. I'm going to put back my lone pair, otherwise it would send a wrong message. And also I'm going to mark down all other lone pairs. Now this is our Lewis dot dash structure for the given formula. Let's go for our next question. We have cyanide ion. In this ion, which atom hold the negative charge? Carbon is group 14, so it holds 4 valence electrons. Nitrogen, group 15, it is going to hold 5 valence electrons. We have a negative charge, which adds one more electron. That brings in a total of 10 valence electrons. Now I can put carbon, nitrogen, connect with a pair of electrons 1, 2, and I'm going to place rest of the electrons. So 3, 4, 5, 6, 7, 8, 9, 10. Now this structure I have come up with doesn't look right. Why? Because even though nitrogen has completed its octet, carbon has not. Remember, in period 2, carbon, nitrogen, oxygen, fluorine, they will always go for 8 electrons. So we can do a small rearrangement. If you want to calculate formal charges, go ahead and try that. You will find in this structure that carbon is going to hold a +1 charge, and nitrogen will hold a -2 charge. Now, why did we even started drawing these Lewis structures? The reason is we are asked to find which atom is holding the negative charge. So you have to know that you have to come up with the formal charges. If you want to come up with the formal charges, you actually have to have some sort of a Lewis structure in your hand. So that is why we are doing the Lewis structure. So the first step in solving this problem is coming up with the proper Lewis structure. So now we know this structure doesn't work right. So we'll move a pair of electrons. Now you have to know that you cannot just pick a random pair of electrons and move it. Think logically. If you try to move, this is the only left pair of electrons on carbon. So if you move this pair of electron to the center, it is not going to help carbon, because carbon really needs to complete its octet, and if you share this again with nitrogen, it is not going to help. So you have to think that if you are moving any pair of electrons, it should be from nitrogen. So I'm going to move a pair into the center like that. Now I'm going to come up with a layout like this. Now even in this structure, I can see my nitrogen has completed its octet, but oxygen is still carrying only 6 electrons. If you do the formal charge calculations, you will find that carbon has a 0 formal charge and nitrogen has a -1 formal charge. So I'm going to do another rearrangement where I move this pair of electron there. Now my structure is going to look like this. Now both carbon and nitrogen atoms are happy because their octet is complete. So this will be our proper Lewis structure for cyanide ion. And then you can find the formal charge. You will find that carbon has the formal charge of -1, and nitrogen will have the formal charge of 0. So which atom hold the negative charge in the cyanide ion? That would be carbon. Now this is also another example that shows that completing octet is much more important than the formal charge. Why am I saying that? Look at the second structure. In the second structure, you will see carbon holding a 0 formal charge, while nitrogen holding a -1 formal charge. And when we were learning about formal charge guidelines, we said that we try to minimize the formal charge as much as possible, and when there are charges, we try to assign negative charges to the more electronegative atoms. Considering carbon and nitrogen, think about the periodic trends. Nitrogen is more electronegative, and here nitrogen is holding a negative charge. So it feels like this is a good structure because carbon has a 0 formal charge, the minimum, and the negative charge is negative formal charge is assigned to the more electronegative atom. So it feels like this one is the right one, but no. Completing octet for the elements like carbon, nitrogen, oxygen, fluorine is much more important than chasing the formal charge. So that is why we ended up with this as the correct Lewis structure, and in that the carbon carries the -1 charge. The molecules BF3 and NF3 have similar formulas but different molecular structure. Explain. In the periodic table, you will find that boron and carbon in the same period number 2. In period number 2, starting from carbon, this set will always go for octet. However, things like beryllium boron can make electron deficient compound. They don't have to go for octet all the time. They're fine with electron deficiency, but if they find an opportunity to fill it, they would do it, but still they can make electron deficient compound without going for octet. However, carbon, nitrogen, oxygen, fluorine will always go for octet. Now the two elements we are looking at is boron and nitrogen. The Lewis structure of BF3 will look like this. You can find, if you want, you can find the total number of valence electrons and place them, but you're going to end up with that structure for BF3. And then going for an F3, nitrogen 5 valence electrons, fluorine 7, you have 5 of them. And the Lewis structure of NF3 looks like this. When you examine the electron domains or the repulsive units, the VSEPR units around the central atom, for BF3 you will find 3 repulsive units, but for NF3 you will find 1, 2, 3, 4 repulsive units. Or VSEPR units. If you have 3 repulsive units, your electron pair geometry is going to be trigonal planar. So BF3 will have a trigonal planar geometry for the electron pair geometry, and since everything is in the bond form, so your geometry and the shape both the same thing. But in the case of NF3, since you have 4 VSEPR units or repulsive groups, you're going to have a tetrahedral geometry. So at the end, even though BF3 and NF3 have pretty similar formulas, their molecular structure is going to be different because they have different repulsive units. The geometry around the central atom is different. BF3 has a trigonal planar geometry, while NF3 has a tetrahedral geometry.